Assalamualaikum warahmatullahi wabarakatuh. So today my group, which is member Mazir, Manisha, Ardo, Olivia, me and Hasna, will present a Midproject. I will explain 9.1 ABD. Atomic radius. Atomic radius decrease across the period. This corresponds to the increase in the number of proton and electron. The electron copy the same principal quantum shell. This increase the overall nuclear charge. So now the proton are pulling on the outer shell electron, making the element more tightly bound. Ionic radius increase across the period because the ratio of proton to electron become greater. Cation are smaller than their neutral atom. Anion are always larger than their neutral atom. When elements are isoelectric, the rule that the higher the nuclear charge, the smaller the ion appears. The melting point of a substance is the temperature at which a solid and liquid phase may coexist in equilibrium and the temperature at which matter change from solid to liquid form. The term applies to pure electric conductivity. Can be defined as how much voltage is required to get an amount of electric current to flow. This is largely determined by the number of electrons in the outermost shell. This electron determines the ease with which mobile electron and generate. Point B. The atomic radius is the resistance from the atomic nucleus to the outermost stable electron of a neutral atom. In practice, the value is obtained by measuring the diameter of an atom and dividing it in half. The radius of neutral atoms range from 30 to 300 pm to or trillions of a meter. The ionic radius is half the resistance between two gas atoms that are just touching each other. Value range to 30 to over 200. Is a neutral atom. The atomic and ionic radius are the same, but many elements exist as anions or condition. Point D. First, ionization energy varies as CONF is ionization energy increase on going from left to right in a period due to increase in effective nuclear charge and decrease in radii. However, ionization energy of N is greater than O because P subshell in N is exactly half filled and has greater stability.
The next is C, is variation in melting point and electrical conductivity. The first is simple molecular. The melting point is low. The simple molecular substance generally have low melting point, are often liquids or gases at room temperature. So the melting point is in room temperature. The next is electrical conductivity. Is simple molecules have no overall change or charged particles that can separate. So simple molecular substance cannot conduct electricity even when liquid or dissolved in water. The next is giant molecule. The melting points have high melting points because a lot of strong covalent bonds must be broken. Graphite, for example, has a melting point at more than 3600 Celsius. Next is electrical conductivity. Diamond has not conduct electricity, whereas graphite contains free electron, so it does conduct electricity. Silicon is a semiconductor. It is midway between non-conductive and conductive. Next is metallic bonding. The melting point, as metals are giant lattice structure, the number of electrostatic force to be broken is extremely large. And so metal have high melting and boiling points. And the electrical conductivity, metallic bonding conduct electricity is because they contain charged particles that are able to move.
Properties of ceramics in terms of their chain structure. Strange. The strong bonds holding the atoms or ions together in 3 dimensions will make the ceramic hard and strong, but also brittle. Think about the ceramic or of floor tile as a simple example. The tile is obviously hard and you can stand on a floor tile or place heavy furniture on without it breaking, so it is strong. The other hand, it isn't difficult to break a tile in half by snapping it, especially if you score a shallow line on it first with a cutting tool. It is brittle. The melting points. Ceramics have high melting points because of the need to break the strong covalent or ionic bonds holding the giant structure together, and it takes a very high temperature to do this. The electrical conductivity. Most ceramics are good electrical conductors. If they are covalent, there are no free electrons to move around. If they are ionic, the ions aren't free to move in the solid. And the example is magnesium oxide. Ceramics made from magnesium oxide are used in almost other things. The first is furnace linings or refractory bricks, and the second is heating elements, and for example is the electric cookers, and the third is a heating element will often have a metal core which heats up when an electric current flows through it. And then the second is aluminum iodide. Various web sources describe this as the most important iodide ceramic. The use of aluminum iodide ceramics include 1. The high temperature and high voltage electrical insulator. And the second is replacement hip joints. Hip joints are a ball and socket arrangement, and the ball or socket can be made of aluminum iodide ceramic material. And the last is large amount of energy needed to separate the ions. And the third example is silicon dioxide. Uses of silicon dioxide ceramics include the first is a furnace cleaning of refractory breaks in a furnace for the production of glass, because the giant covalent structure has a very high melting point to the strength of the SEO covalent bonds in 3 dimensions. And the second is to make ceramic tiles to protect the space shuttle. The tiles are light and have a melting point.
The 9.2 periodicity of chemical properties of the elements in period 3, and I am in charge for the A part. So the first one is reaction with oxygen gas, which is O2. The first one is sodium. Sodium burns on heating with an orange-yellow flame to form white sodium oxide, which is 4Na plus O2 equals to 2NaO2 and A2O. And then the second one is magnesium, burns on heating with a brilliant white flame to form white magnesium oxide, which is 2Mg plus O2 equals to MgO. And the third one is an oxide layer, will form on the aluminium when it is exposed to air. This oxide layer prevents aluminium from reacting. However, if powdered aluminium is used, it burns on heating with white flames to form with aluminium oxide, which is 4Al plus 3O2 equals to 2Al2O3. And then the fourth is phosphorus, burns on heating with a white flame to form clouds of white covalent oxides, phosphorus 3 oxide and phosphorus 5 chloride. And if oxygen gas is limited, so it is P4 plus 3O2 equals to P4O6. And if oxygen is in excess, then P4 plus 5O2 equals to P4O10. And then the fifth is sulfur burns on heating with a blue flame to form sulfur dioxide gas, which is S plus O2 equals to SO2. And under suitable conditions, sulfur dioxide can be converted to sulfur trioxide, which is 2SO2 plus O2 equals to 2SO3, and this is a reversible reaction. And then next is reaction with chlorine gas, which is Cl2. The first one is sodium, burns on heating in chlorine gas with an orange-yellow flame to form with sodium chloride, which is 2Na plus Cl2 equals to NaCl. The second one is magnesium, burns on heating with chlorine gas with a brilliant white flame to form white magnesium chloride, which is Mg plus Cl2 equals to MgCl2. The third is aluminium, burns on heating to form ionic aluminium chloride, which is 2Al plus 3Cl2 equals to 2AlCl3. At temperature about 180 degrees Celsius, aluminum converts to a molecular form, which is Al2Cl6, a dimer of covalent AlCl3. At even higher temperature, Al2Cl6 breaks into simple AlCl3 molecules, which is 2Al plus 3Cl2 equals to Al2Cl6. The fourth is silicon, burns slowly in chlorine gas at red heat to form covalent silicon 4 chloride or silicon tetrachloride, a colorless liquid which vaporizes. It is Si plus Cl2 equals to SiCl4. The fifth is phosphorus, burns in chlorine gas to produce a mixture of two chlorides, phosphorus 3 chloride, PCl3, and phosphorus 5 chloride, PCl5. In excess chlorine gas, PCl5 is the major product. PCl3 is a fuming liquid, while PCl5 is an off-white solid. So if chlorine gas is limited, then it is P4 plus 6 Cl2 equals to PCl3. And if chlorine gas is in excess, then P4 plus 10 Cl2 equals to PC4 PCl5. Then the last one is about reaction with water, which is H2O. The first one is sodium catches fire in cold water, and a violently exothermic reaction occurs to form sodium hydroxide and hydrogen gas. It is 2Na plus 2H2O equals to 2NaOH plus H2. The second one is magnesium reacts very slowly with cold water, taking several days to collect a test tube of hydrogen gas and a weakly alkaline magnesium hydroxide solution, which is Mg plus 2H2O equals to MgOH2 plus H2, which is very slow. However, it reacts very rapidly with steam to produce magnesium hydroxide and hydrogen gas, which is Mg plus H2O equals to MgO plus H2, which is very fast.
Part B. Variation of the oxidation number in the oxide. The oxygen in the compound is always the more electronegative element, and so always has negative oxidation number. In each case, it usually minus 2. The oxidation number of the other elements in each of the following: Na2O, MgO, Al2O3, SiO2, P4O10, CSO2, and SO3. The pattern is much the same as before. The maximum oxidation state shown by the elements in this period is the same as the number of other electrons. In the case of sulfur, the maximum oxidation state is plus 6. All of the sulfur's 6 outer electrons are being used to make the bonds in sulfur trioxide, but that doesn't have to be the case. In sulfur oxide, where sulfur has an oxidation state of plus 4, only 4 of its outer electrons are involved in bonding. In compounds between sulfur and chlorine, the highest oxidation state shown by the sulfur is +4, not +6. In other words, have SCl4 but not SCl6. There is, however, a compound sulfur fluorine 6, so sulfur only show its maximum oxidation state when it is combined with oxygen or fluorine. Okay, second is variation of the oxidation number in the chlorides. The chlorine in the compound is the more electronegative element, and so the chlorine always has negative oxidation number. In each case is -1. The oxidation number of the other element in each of the following compounds: NaCl, MgCl2, Al2Cl6, CiCl4, and PCl5. In each case, the oxidation number is the same as the number of electrons in the other energy level of the atom in question, their valence shell electrons. These compounds are involve the element using all of its other electrons in the bonding, either giving them away to form positive ions or shedding them to form covalent bond. In each of these cases, there is a movement of electrons away from the element towards the more electronegative chlorine. That is why all of these oxidation numbers are positive. The phosphorus case a little bit further because phosphorus formed two chloride PCl3 and PCl5. The oxidation number of the phosphorus in PCl3 is +3. The point to make is that the maximum possible oxidation number of an element in period 3 is going to be the same as the number of electrons in its other energy level, but the smaller oxidation number are also possible where not all of the other electrons are used.
Oxide is a chemical compound in which an oxygen is combined with another element. Most metal oxide react with water to form hydroxide ion and resulting in a basic solution. Most non-metal oxide react with water to form acid and resulting in an acidic solution. Sodium oxide and magnesium oxide is a strong basic oxide. It is a basic because it has an oxide ion. An oxide ion has a very high tendency to react with hydrogen ion, resulting in a hydroxide. Sulfur oxide is a relatively weak acid oxide. Sulfur dioxide is fairly soluble in water, and when reacted with water, it results in an acidic solution that is sulfurous acid. This is because of the less electronegative ionic metal oxide, and it has a very weak bond with the oxygen ion. And the oxygen ion is more easily given up to react with hydrogen ion, forming a hydroxide ion. Non-metal oxide have a strong covalent bond with the oxygen, so it keeps themselves together better than the metal oxide, and more hydrogen ion is generated. Silicon is too similar in terms of electronegativity with oxygen to form an ionic bond. So it does not have an ionic bond and it does not have an oxygen ion. Instead, it will form a covalent structure and it does not react with water. Aluminum oxide is not soluble in water and does not react with water. However, aluminum oxide is amphoteric, meaning it can react as a base or an acid depending on the reaction. For example, when it reacts with sodium hydroxide, it will act as an acid to form sodium aluminum oxide. Chloride is defined as any chemical compound that contains a chlorine ion in its chemical composition. Covalent chloride, like aluminum, silicon, and phosphorus chloride, will react with water and gets hydrolyzed, resulting in an acidic solution that contains hydrogen chloride, while ionic chloride, like sodium and magnesium chloride, will simply dissolve in water. It is because covalent chloride does not have enough electronegativity difference to form an ionic bond with the chlorine ion. So it is because that it doesn't form an ionic bond, it will instead form a covalent bond with the chlorine. Because it is a covalent structure, it does not conduct electricity because of the lack of ion.
Interpret the variation and trend in 9.2 F and G. And first, oxidation number of period 3 oxide or chloride correspond to the number of electrons used for bonding. It is always positive because oxygen is more electronegative than any of the elements. For example, I in SO2, S has oxidation number +4 because only 4 electrons are used for bonding. And 2, in SO3, S has oxidation number +6 because all 6 electrons are used for bonding. In general, electronegativity increases periodically from left to right and decreases from top to bottom. And this table 2, the trend of electronegativity is Na is the lowest. It will increase as we move to the right. Cl is highest and there is none in Ar. In this table 3, bonding in chlorides Na and Mg are ionic. Al until Cl are covalent and none in argon. Bonding in oxides Na until Al are ionic. Si is covalent bracket 3 minus D network. P until Cl are covalent molecular and none in argon. And so this the types of chemical bonding present in chlorides and oxides from observation of their chemical and physical properties. Study the characteristic properties of an element in a particular group using knowledge of chemical periodicity. In this presentation, I'm using chloride element. For the group, chloride is 17, period is 3, block P, atomic number 17, state at 20 Celsius is gas, electron configuration 3s23p5, and melting point minus 101.5 Celsius and minus 150.7 Fahrenheit, 171.7 Kelvin. Boiling point minus 34.4 Celsius and minus 29.27 Fahrenheit and 239.11 Kelvin. Density 0.00298 and relative atomic mass 35.45 and K isotopes 35 Cl and 37 Cl. S number is 7782 and minus 50 minus 5. Deduce the properties possible position in the periodic table and the identities of unknown elements from the information given about their physical and chemical properties. For the element that I use is sulfur. For image explanation, for the sulfur is fire and brimstone's background. And for the appearance, there are several allotropes of sulfur. The most common appears as yellow crystal or powder. And for the sulfur history, sulfur is mentioned 15 times in Bible and was best known for destroy Sodom and Gomorrah. It was also known to the ancient Greeks and burned as a fumigant. Sulfur was mined near Mount Etna in Sicily and used for bleaching clothes and preventing wine, both of which involve burning it to form sulfur dioxide and allowing this to be absorbed by wet clothes or the grape juice. For centuries, sulfur, along with mercury and salt, was believed to be component of all metals and form the basis of alchemy, whereby one metal could be transmuted into another. Antoine Lavoisier proved that sulfur was an element, but in 188, Humphrey Davy said it contained hydrogen. However, his sample was impure, and when Louis Joseph Gay-Lussac and Louis Jacques Thénard proved it to be an element the following year, Davy eventually agreed. And for the biological role, sulfur is essential to all living things. It is taken up as a sulfate from the soil or seawater by plants and algae. It is used to make 2 of the essential amino acids need to make protein. It is also needed in some coenzyme. The average human contains 140 grams and takes in about 1 gram a day, mainly in proteins. Sulfur and sulfate are non-toxic. However, carbon disulfide, hydrogen sulfide, and sulfur dioxide are all toxic. Hydrogen sulfide is particularly dangerous and can cause death by respiratory paralysis. Sulfur dioxide is produced when coal and unpurified oil are burned. Sulfur dioxide in the atmosphere causes acid rain. This can cause lakes to die, partly by making toxic aluminum salt soluble, so that they are taken up by living things. And the last, natural abundance. Sulfur occurs naturally as the element often in volcanic areas. This has traditionally been a major source for human use. It also widely found in many minerals, including iron pyrites, galena, gypsum, and Epsom salt. Element sulfur was once commercially recovered from wells by the fresh process. This involved forcing superheat steam into the underground deposit to melt the sulfur, so it could be pumped to the surface as a liquid. Modern sulfur produced in almost entire from the various purification process used to remove sulfur from natural gas, oil, and tar sand. All living things contain sulfur, and when fossilized, as in fossil fuels, the sulfur remains present if unpurified fossil fuels are burned. Sulfur dioxide can enter the atmosphere, leading to acid rain. So that was my group presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.